And I'm going to start with the presentation, which is here. Okay. I suppose you can see my screen now, which has the ELECTRA paper on. Please let me know if you don't. So I'm going to present ELECTRA pre-training text encoders as discriminators rather than generators. And this paper, I found it very interesting in multiple aspects, but I'm going to save that for last. So first I'm going through the paper, then I'm going to explain why I like this paper so much. So firstly, what is the problem that this paper actually wants to solve? Before I explain what is the problem that it's trying to solve, let me go first through what is the state of the art, or, well, the state of the art-ish for this problem, which is BERT, the language model that many of you have probably heard of. So to explain BERT, I'm going to use this image because it's easier to follow as an image. So BERT is a language model where you want to generate embeddings for words. But to train the model, it's much easier to access a large data set if the learning mechanism is self-supervised. So you don't need to have humans to generate labels. The labels would come from the problem itself. To do that, BERT does the following. So you take a sentence and you separate the tokens of the sentence. In this example, the chef cooked the meal, and then you mask about 15% of the words. And the learning task from BERT is to reconstruct the word that is masked. So you pass BERT this sentence, mask chef, mask the meal, and ideally it would reconstruct. It would say that this mask corresponds to the, and this mask corresponds to cook. And this is BERT in a nutshell. So now, what is the problem that this paper is trying to solve? They realize that these language models are very, very expensive to train. So they work very well in practice, but you need couples of days in very expensive hardware in order to train a model. Furthermore, some other papers have realized that the compute power that you spend on the model is related to the performance of that model. This means that the more money you have, the better model you can create. So they try to tackle this problem from the other way around. What can we do if you don't want to spend more money and want to have better models? Essentially, how can we improve the computation efficiency of this learning paradigm? Furthermore, they also realize that BERT has a few problems, but these sort of problems are not tackled in this paper alone. They also grab a few ideas from other papers, such as BERT is trained with these mask tokens, but in practice they don't exist. So you spend a lot of computation trying to represent what this mask thing is, which is very prevalent in the pre-trained task, but then the mask token does not exist in practice. So there is a mismatch between what BERT is trained on and what appears in practice. But the main purpose of the paper, ignoring those tiny details, is essentially to make training BERT or BERT-like models more efficient. So the question is, how do they do that? So again, I'm going to use image 2 because it's the most simple way to explain ELECTRA in a nutshell. So I'm going to explain an overall what's the thing they are proposing, then I'm going through the details. So the overall thing is, instead of trying to reconstruct the mask, they create a generator which has the same architecture as BERT to regenerate the original text, or regenerate the probability distribution for each mask. From that probability distribution, they can sample. For instance, if the generator, you apply the generator to this masked sentence and you then sample, you might obtain the chef ate the meal. So in this case, it was able to reconstruct the first word, but the third word, or the second mask, was incorrectly reconstructed. Then they train a discriminator to classify whether each token is part of the original sentence or is a replaced one. So it's a binary classification, very simple. They do this over the same pre-training task as BERT or the other similar models. But by the end of that training, they crop this thing, they discard the generator, and they keep the discriminator alone. So in essence, you have, instead of one model, now you have two models, and one is just an auxiliary step. So you are going to discard it completely. And they actually kick off the paper showing that showing essentially this image, which is a summary of the results they obtained in this paper. And this image on the x-axis, you have the pre-trained flops or floating point operations, essentially the compute power spent training this. On the y-axis, you have the glue score, which is a typical score for NLP models. And so what you see here very quickly is that ELECTRA, for several model sizes, which we'll go through later in this presentation, outperforms for the same pre-training flops the existing models at several scales. So, and the difference is particularly big if you compare this point here, which corresponds to their biggest ELECTRA model, against XLNet. So it is 0.7 to the power times 10 to the power of 20 flops versus 4 times 10 to the power of 21. So it's roughly 5 times more flops, which is a very big difference. They are essentially saying that you can obtain the state of the art spending 1/5 of the computation power, or alternatively, you spend as much computation power and you get a better model. So essentially, they are proposing a win-win thing. So how were they able to reach to these win-win states? And this is actually one of the parts I like the most about this paper, is that they go step by step about the things they tried and either work or didn't work. And they explain the things that worked, and they theorize why certain things didn't work. So again, coming to the ELECTRA, essentially you have two models, one that regenerates the masked tokens, and because it regenerates the full probability distributions for each masked token, then you can sample from it. And then you have a discriminator that takes each token and tries to assess whether it is an original token or a replaced token. What else do we need to know here? So a few important details that help them achieve this performance. Firstly, if the generator happens to sample the correct token, you'll see that the label corresponds to the original token and not to a replaced token. This is very important because you don't want to confuse the discriminator. And confuse is an important word to be used here, because you'll see in the section 2 that they mention GANs multiple times. And GANs, if you have looked into how they work, essentially you also have two models, one generator and one discriminator. But in the GANs, the generator wants to fool the discriminator. And here they are trying to cooperate. They are not working against each other. And this is an important distinction, because in the GANs, the loss of the generator is related to how much they can fool the discriminator. And here, the loss of the generator is standalone. So they still want to reconstruct the text correctly. So you can.
Question?
Yes, of course, Arvid.
The generator, does it predict or does it sample every word independently? Or say you could imagine that when you have two masked out tokens, that you have groups of words that fit better together, so that maybe the and cooked could be compared to a and I don't know, some other verb that fits better in that context, or does it just independently sample each mask point?
So to answer your question, in one, well, I can't say they are independent because so this is a bidirectional transformer. So you'll have information about the other mask token in the first mask token, and you have information about the whole sentence in each mask. So I don't think they are in the, so the probability distributions are not independent, but when you sample them independently. I don't know if I'm making.
Actually, because for the discriminator, it would make a difference, right? So it might be perfectly sensible for a certain sample to be classified as correct if they have been sampled from the same modus of the probability distribution, but completely nonsensical if they've been sampled independently. I don't know.
I see. I actually, I don't think they mentioned that, but I think that makes a lot of sense. So if I got it right, what you're saying is that if you sample, in this case, they sample the and 8, but if they were to sample potato and I don't know, fly, they would see that those two words do not make sense compared to the rest, so they are easy to discriminate.
Yeah, but if it's like the airplane flies, that would of course make sense again, because together they are more meaningful than apart.
Yeah, exactly. I don't think they mentioned that throughout the paper. At least I don't remember seeing that, but I think it makes a lot of sense if they were to do that.
Cheers.
Thank you for the question, Arvid. Again, if you have questions, comments, please feel free to just speak out loud. This is meant to be a discussion and not a one-way presentation. Carrying on with the paper. So as I was saying, as opposed to GANs, the loss of the generator, or the generator is trying to reconstruct the words and not to fool the discriminator. So that's why you see GANs so much. They essentially present GANs as a similar architecture, but there are important differences that we need to take into account. Another important detail is that they generate the probability distribution for each mask, but as it is related to the question that Arvid made, they do not simply pick the argmax for each mask. They actually sample the thing. So you can, for the same sentence, same masks, same input weights in the generator, you can obtain many different outputs. So a question that I haven't tried to assess so far is the following. So I said that the point of this paper is to try to make things more efficient. So why is this more efficient? Why is BERT slower than this thing? Because this thing even has 2 models, and one of the models is supposed to work like BERT. So how the hell can they make it faster? So in BERT, the loss is computed from the ability of the generator to reconstruct this thing. So they have the whole thing gets trained on these 15% of the masks that they take. So you have the work to generate the embeddings for each word to propagate inside the complex transformer architecture, but in the end, you only use 15% of the things to train your model, those masks. And in this scheme, you might have more operations because now you have 2 models and you need to do this whole thing. However, you actually train the model that you use in the end using all the tokens in the input. So you use both the mask tokens and the unmasked tokens. And they theorize that because now you are using 100% of the tokens to train your system, the thing becomes more efficient. And that's why you can extract more performance with less computing power, although this is a more complex scheme. More important details. Let me go through my notes to just double check I didn't miss any important detail. So one thing that you see in this image, and you'll see in the next section, is that the generator is smaller than this discriminator. They actually tried multiple things that will go in a second, but they go with a smaller generator. So essentially, this not only saves costs, but it also has some other nice properties that we'll see in the future. Because remember, this generator goes away after the pre-training task. They only keep the discriminator. So the smaller you can make this bit without losing performance here, the better you will do in the thing they are trying to assess, which is glue metric performance versus expense to compute to train the model. More important thing. So this thing wants to reconstruct the word. So it's a softmax with one output for each possible word, and the discriminator is a binary classification problem, super simple. So they define some equations about this problem, which are pretty standard. And then you see that the loss of the generator, which is this bit, is the softmax, because remember, they just want to reconstruct the masked word. This is similar to BERT. And here you have the loss of the discriminator, where it is the sigmoid function. So it's a binary classification problem. And an important detail here is that while they are training, they are jointly training the two models. So they want to minimize the sum of the loss for the generator, which is this part, plus some weight times the loss for the discriminator. And if you go to the appendix, they say that they use this lambda equals to 50 because of an important detail. The softmax of the generator, they say that they use 30,000 classes, and here is a binary classification. So necessarily the numbers you'll see here, because you have many classes, will be bigger than the numbers you'll see here, because it's a binary classification problem and it's kind of balanced. So they use between 15 and 25% of masks. So they need to bring up the proportion of the loss of the discriminator, also because you want to keep the discriminator in the end. So if you have to sacrifice performance in one side of the model, you would like to sacrifice performance in the generator, not in the discriminator. And this,
yes, the generator loss, I didn't quite understand it. So it is essentially saying the generator predicts a probability for a word. Yes. And for that word, we know what the real word is. So we essentially punish if the predicted probability is too small.
Yes.
And the sigmoid is within the PG.
The sigmoid is within
or softmax. So the softmax is within the PG. You mentioned softmax. I see.
Yes.
Okay. Thanks. That's it.
Okay. Yeah. So yeah, you have you want to, because as opposed to normal GANs, if this was a GAN, you wouldn't see these here. But because this is not a GAN, you want to maximize the likelihood of picking the correct word. Therefore, they apply the softmax to attempt to reconstruct the probability distribution for each mask. Does this make sense, Arvid?
Yeah, I think it does. So it tries to minimize the expected surprise of that generator. Yeah, thanks. Very helpful.
Thank you, Arvid. So by now, you have probably realized that these two things are trained at the same time. So they start as garbage at the beginning, both. So the generator is a garbage and the discriminator is a garbage, and they gradually improve over time. And we'll see in a bit that this is an important detail to keep into account. So now let's go through their experiments where, well, this is not a typical experiment section in the sense that they also explain many things that they've tried and many combinations of what turned out to be ELECTRA. So to start this section, first, let's keep in mind that they want to compare their thing to BERT. They want to show that their thing is more efficient, more compute efficient than BERT for the multiple sizes of BERT, because you can have BERT with multiple sizes and they have very different computational requirements. To enable a fair comparison, they just start this section by saying we'll use the same hyperparameters as BERT, except a few details here and there. So the discriminator you obtain at the end of this whole setup is pretty much the same as BERT. So they start by theorizing the following. So you have two models, the generator and the discriminator, and you can make them be exactly the same thing. So you can make the two things to have the same weights. So they start by proposing weight sharing. What if we have like two exact same models, but one wants to, as the loss function, to try to reconstruct the words, which essentially is BERT, and the other one is trying to discriminate whether the word was masked and then sampled with a different thing or not. In their results, they'll see that if you do this, if you make them be the same size and share weights, and if you fix the computational power that you are able to spend in this scheme, you'll not get the best performance. So they decided to decouple the two models. Then they tried to make them completely separated, but they also didn't see the best performance. So then the final outcome that they described and that they actually applied in the ELECTRA is to tie the embedding. So the generator and the discriminator, for the same word, they generate the same embeddings, and that embedding part is kept together between the two models. The rest is different. So in this image, they show for multiple discriminator sizes, output sizes, embedding sizes, if I'm not mistaken. Or no, hidden layer sizes, sorry. These numbers you'll see are the size of the hidden layer. So for multiple discriminator sizes, they experimented with multiple generator sizes. And what they have concluded is that their scheme performs as the best performance when the generator is slightly smaller than the discriminator. So here you see that for a discriminator with size 512, the best generator has a size of 256. And you'll see the same relationship for the other sizes. So now coming back to the image on top, the generator is smaller than the discriminator, and that's why they made a smaller square here, because they verify that they get the best performance with a slightly smaller generator. And also remember, the generator is going to be discarded, so whatever compute you spend with the generator is going to be wasteful. So if you are able to minimize your compute here, that would be great. However, if you have a crap generator, then your discriminator will not be able to learn. So you need a balance between the two things. And remember that I said that they both start as garbage and they learn progressively. And now you know that the generator is smaller. So in essence, what you'll see while you're training the model is that the discriminator starts with a very easy task. So they'll start with garbage samples. So it's very easy to discriminate. And as the generator gets better, the discriminator will get a harder task. So it is able to learn progressively as your training routine goes on. And because the generator is smaller, the task is simplified compared to if the generator had the same size. So it's not only to save compute power, but the fact that the generator is slightly inferior to the discriminator enables the discriminator to learn better. Otherwise, the task would be too difficult and the discriminator wouldn't be able to learn. I have a question in the Q&A from Dwayne, which says, this is a question, do you mind if I'm going to read. This is a question for a discussion at the end, as we have large BERT models whose weight we can download. If we use to download BERT large model to replace the generator, would we expect the newly trained model to be BERT? Okay, I think so. What Dwayne is answering is asking is the following: what if instead of having a generator and training the generator as we go along, what if we just download BERT and put BERT here and hope for the best for the discriminator? So they mentioned in this paper, they don't provide proof, but they theorize that the fact that they both start with poor capabilities and they grow together, it makes the discriminator to have progressively harder problems, but they are always solvable. If we were to put BERT as a generator, the problem would be too hard for the discriminator to start learning, and therefore it wouldn't be able to learn. That's what they theorize in the paper, but I don't think they provide much proof or experiments to that. So they mention curriculum learning, which is essentially this scheme of having things to learn with progressively harder problems. I hope this answered your question, Dwayne. Continuing with the presentation. So yeah, so I've explained why the generator is smaller and why what's important for the why is that important for the generator to be smaller? Not only to save compute power, because remember at the end we just want to get better models with less compute power, but also because it helps the discriminator to actually learn what's going on. The next thing they tried was multiple training approaches, which you can see on this image on the right. So they start with BERT, which is this dashed green line, which has this performance. The x-axis is compute power spent. The y-axis is the clue score. So the first thing they compare to is to this two-stage ELECTRA. What is this two-stage ELECTRA? So let me see if I still got it right. Oh yeah, it's this one. So this this two-stage ELECTRA is to train the generator for a few steps, then initialize the discriminator with the weights of the generator, and train the discriminator while keeping the generator frozen. So it's also similar to the question that Dwayne asked: what if we just downloaded BERT and then train the discriminator? I think this is very similar to this two-stage ELECTRA. So they first train a generator. If you were to download BERT, you would get to this point, and then they train the discriminator. So they are able to outperform the standard BERT by doing this, but it's not enough to beat the best performance that they obtained. The orange line you'll see here is the adversarial ELECTRA. So remember, I said in this image above that this is very similar to, again, a generative adversarial network. But in again, the loss you'll see associated to the generator essentially makes the generator want to fool the discriminator instead of just trying to do his own thing and reconstruct the words. So if you do an adversarial generator, you'll see good-ish performance. You are able to outperform BERT. However, it's not good enough compared to the ELECTRA they are proposing here, where the generator wants to cooperate. Well, the generator doesn't see the discriminator, but in essence, you can imagine them as cooperating. The generator wants to reconstruct words, and the discriminator wants to see whether the reconstructed words were the original ones or not. And these are essentially the main experiments that worked and they did with the paper. Now they at this stage of the paper, they go through the results with more detail, and they want to show us that the models you obtain here are definitely better than BERT. So in table 1, they compare what they call small models. And what you can see in table 1 is if you compare what they call the ELECTRA base versus BERT base, they'll have the same training requirements and inference requirements, because remember, the discriminator you obtain at the end is pretty much the same as BERT, because it also has the same hyperparameters. So you can see that they take the same computing budget. However, the glue score you obtain for ELECTRA is superior to the glue score you obtain for BERT. If you were to do smaller versions of this ELECTRA model, you will always see the same relationship. So you'll have, for the same computing power, you'll have a better glue score, or you can have the same glue score and spend less computing power, whatever floats your boat. And you can decide what is best for your problem given your resources. So it's more efficient for small models. Now, the important question, does this also work for big models? And for that, you'll need to check table 3. And in table 3, they compare a larger version of ELECTRA. This is not the ELECTRA base of the table before. This is a ELECTRA with more training steps, and I think it has the same size, but it has at least way more training steps. And you'll see that compared to XLNet, which is not the same as BERT, you'll see that you still need more compute power to train the XLNet. However, you'll have better average glue scores with ELECTRA. So again, they have answered the question. Does this also work for large models? The answer is yes. However, in my opinion, if you look at table 3 and table 1, the difference is bigger for smaller models. But keep in mind that what they call a small model requires 4 days in 16 TPUs. So I wouldn't say this is a small model, but well. So yeah, they have shown essentially that ELECTRA outperforms BERT for small scales and large scales. So win-win, right? Final question. They knew by now that the results were better, but why were they better? Is it because they did this 2-model scheme? Is it because they now have a loss that goes through all the words? To answer that question, they made the experiments they described here, which I'm going to summarize with the help of this table. So imagine you have BERT. So BERT is your baseline here. To compare against BERT, they decided to create what they called ELECTRA 15%. So this is the same as ELECTRA, but instead of getting the loss for all the words in the input, it's trying to discriminate whether they were replaced or not, they just use the loss for the masked tokens. So by now you have, so repeating again, instead of having the loss for all the input tokens, now you only have the loss for the input tokens that were replaced. And the difference in performance was very small. So replacing BERT by ELECTRA, in other words, doing this 2-model scheme, but just computing the loss in the discriminator for the replaced tokens will not get you far. You'll get a slightly better model for the same compute power, but the difference is very small. The second experiment they did, they called replace MLM, which is the same as BERT, but instead of having those masked tokens, so going to page 1. Figure 2. Instead of having these tokens, you'll just have this sampled output from BERT. So you'll try to reconstruct. In this example, you'll try to reconstruct cooked, given that you know that you want to reconstruct this thing. So you're given the rest of the context. And if they do this, in other words, instead of trying to reconstruct the mask, which is a fixed token for whatever you are trying to reconstruct, you are going to reconstruct the position for which you also have a sample. And if they do that, and go to table 5 again, this one. If you do that, you'll get the similar gain as converting to ELECTRA 15%. So again, not a big difference. Then they did an experiment that they called all tokens MLM, which is the same as replace MLM, but now they also have some loss term to try to identify the input tokens. So this is a single model, not two models, not a generator and discriminator. This is a single model, and that single model has two loss terms. One that is the standard BERT, but with the replaced tokens, not with the mask tokens. And you also have another loss term to identify the input tokens. And they saw that this got a big improvement compared to BERT. But this is still a single model. So you can see this as if you were to do ELECTRA in a single model instead of a generator and discriminator. And then they compare against ELECTRA, and you see that, well, these two have a big jump compared to the standard BERT. So because these two have a big jump compared to the standard BERT, I think it's safe to go with their conclusion, which is the biggest difference here is that we have loss terms that go through all the input tokens instead of having loss terms that only go through the mask tokens. That's why when they start in the abstract of the paper, they say, we'll get a better performance because we use all loss tokens. This paper is kind of a bit, you need to jump around to find all the clues, but it all adds up. So yeah, this is ELECTRA in a nutshell. I hope you have enjoyed the overall presentation of this paper. And I really like this paper. And I'm going to say to you why. So as any good machine learning paper nowadays, they have a proper code base that we can easily access here. So I didn't mean to open, but okay. You are able to reconstruct all their experiments from their repository, which is great. But many papers nowadays have this. What most papers don't have is this. If you go to by the end of the appendix, you'll see this section, negative results. So you'll also have access to the experiments that they have tried and failed. And I think as a researcher, this is very valuable. Also, if you read the whole paper, you'll notice that they use words like perhaps or take this with a grain of salt when they are theorizing things. So they use the adequate language, the adequate level of language for their sentences, which I think is great not to mislead whoever is trying to read and re-implement or improve what they have done here. Questions, comments?
Hi, Joao.
Hi, Bob.
Hey, thanks for the good review.
Thank you, Bob.
Two super simple questions. Do you think they were sandbagging a little bit by not comparing to GPT-2, or was it not available at the time when they did this? And would word2vec be that much lower than GLOVE on the glue score? I just don't know where that would compare, just from kind of historical perspective. And then just to comment, they might be talking about small models, because I think the GPT-3, it cost something like, I don't know, over 10 million to train. It was like a week of 100,000 plus processors. So.
Okay, going by parts. So first, the easiest one. I think that word2vec would be lower in this image. They actually mentioned word2vec in the related work section here. This section, well, related work should be upper in the paper, but well, they mentioned that you can see ELECTRA as a massively scaled up version of CBAL, continuous bag of words, with negative sampling. So I think this places the word2vec in perspective. So word2vec, if they use the word massively, I would say that word2vec is much smaller. So it's to the left in that image. And from my experience, it performs worse than GLOVE. So I would also put it lower than GLOVE. So I would put in the lower left corner.
Okay.
The other two bits, I don't think they mentioned GPT-2 here. They mentioned GPT, but not GPT-2, right? Yeah.
Yeah, it's a recent paper, so.
I don't know if they did it on purpose to try to sweep the problem under the rug. But yeah, I think GPT-2 is pretty big, so it's already like in this quadrant probably. But GPT-3 would be up here, right?
Yeah, it would be way out there. Yeah.
Because we know that it's very, very expensive to train. They don't even release the model. You need to ask OpenAI to use the model in their beta access. I tried to ask for access, but they didn't reply yet, which I'm a bit sad. I don't know if any of you tried to get access to GPT-3.
So the Rasa guys, they got one, and they did an update on the early preview report on it. Find some information.
Thanks, Bob.
Thank you.
Do anyone else has comments, questions? Okay, I'm assuming. Oh, there is something in the chat. I have access to GPT. Oh, I'm probably going to email you, Dwayne, to try a few things. Easy things, don't worry. If there are no more questions or comments, so I'm going to stop recording. Pause. No, where is? Stop sharing, stop recording.